All right, in this lesson for Calculus 30, we're going to focus on section 2.8 in the textbook. And that title of that section is Higher Derivatives. Okay, so we've been studying derivatives. You know what a derivative is. A derivative is a relationship between the variables describing the slope of the tangent line of a curve. So when we talk about a position time graph, let's say, and this is meters, and this is seconds, if this is the graph here, then the derivative at any point would represent the instantaneous rate of change of meters per second, which is velocity. More on that in another video there, okay? But anyways, there also are higher derivatives. So if we talk about this right here, you know what this is, that's the derivative. We've always just called it the derivative. But really, this is the first derivative. Okay, it's the first derivative. There are other derivatives, like this one. That's the second derivative. And it has also a very cool application here. If you take the second derivative, you can find the value of not only velocity, but it's like if you had, the second derivative would be like the derivative of the derivative. So if you had meters per second, which would be the derivative, and a velocity versus time graph, okay, velocity versus time, then, you know, we have, it looks something like this. Then the derivative of that would be the instantaneous rate of change of velocity per time. Well, what's that? It's velocity per time is meters per second squared. And so the derivative of the derivative is, in this case, acceleration. So that's your measure of your acceleration. Again, more on that later. And if you're in physics at all, you know about velocity and acceleration. In chapter 3, we're going to talk more about velocity and acceleration. However, suffice it to say that the second derivative is very, very useful and has a very direct application in real life situations. Of course, we could keep going, the third derivative and the fourth derivative and so on. And I think at some point they just start writing the number there and not actually these prime markers. So, you know, and so on and so on. Really indefinite. Now, if I give you a little example on higher derivatives, let's say we had, you know, y equals 4x to the fourth minus 2x cubed plus x squared minus 5x plus 2. So that's just a random polynomial that I picked. Remember, this is a polynomial. If I took the first derivative, you know how to do that. That's really easy. Power rule and sum difference rules, that's all you do. So this is 16x cubed minus 6x squared plus 2x minus 5. And that's the first derivative. And notice, I haven't written this yet, but you know this is the derivative. That's kind of the Newton notation. So the second derivative in that similar notation would be just like that, y double prime. And this is what I'm going to use quite a bit, because it's really quick and easy to write, and it makes these questions go quicker. So the second derivative is simply the derivative of the derivative. Okay? So maybe we'll write that down here. Second derivative is the derivative of the first derivative. Okay? So that's what the second derivative is. It's the derivative of the first derivative. Now, the third derivative, let's just change that to third derivative. That's the derivative of the what? That's the derivative of the second derivative. And the fourth derivative here, right? The fourth, I just got to change these letters too. The fourth derivative is simply the derivative of the third derivative. Got it? So you're always taking the derivative of the previous derivative. So if I'm looking at this second derivative now, I find this by taking the derivative of this polynomial right here, not that one. Okay, so 16 times 3, what's that? 30, 48, x squared minus 12x plus 2. That's what it is there. See, I took the derivative of the derivative. Could I keep going? Absolutely. What's that? 96x minus 12. And could I go even further? You betcha. 96. Awesome. And, yes, 0. And every other higher derivative after this will be 0. Okay? But what's really important is that you see that, you know what, you can take lots of higher derivatives, and each of these things will mean something different. And we aren't going to explore all the applications of all these higher derivatives, but really, you know, the first and second derivative for sure. All right, so that's the basic examples there, and what higher derivatives are. Let's get to an example that is a little bit more complicated, because there's a couple little things you got to pay close attention to. So here's the example that we're going to take a look at, and it's going to be this: x cubed plus y cubed equals 5. And I'm going to ask you to find y double prime. So you may be thinking, well, this looks pretty easy. I just take the derivative and then I take the derivative again. And you are exactly right that that's all you do. But in doing that, you're going to find that if this is not just a straight polynomial, you know, f of x polynomial, it gets a little bit tricky. So let's go over a couple things here. The first thing is we're going to need to do implicit differentiation, right? So this is going to be 3x, and this y double prime is obviously, it's d, I shouldn't talk about this notation. What is the second derivative in Leibniz notation? It's d2y over dx2, or d squared y over dx squared. So that's important, and yeah, I didn't tell you about that yet, but that's how you write it in Leibniz notation, okay? But the point is, it's always in reference to x here, so this is going to be 3x squared, because x is our preferred variable, plus, take the derivative of that, that's 3y squared, but because y is not the preferred variable, we need to multiply by y prime, chain rule, right? Equals 0. So you see that y prime, this is what we're trying, we need to find y prime before we get y double prime, so we need to isolate for this right here. So no problem, it's going to be 3y squared y prime equals negative 3x squared. Y prime now, if I divide both sides by 3y squared, I can simplify this now to negative x squared over y squared. So you've got to get the first derivative before you get the second. But, as you know, what we do now is we take now the derivative of the first derivative. So let's change colors, and let's go up here. And so we're going to find the second derivative by taking the derivative of the first derivative. So we look at this right here, and we take the derivative of that. So let's do that, and we have to do quotient rule, don't we? So what's the derivative of this? Well, derivative of the top, and I'll include that negative if you want. You can leave it out front, or we can include it, so I'd like to include that maybe. So let's do that. So the derivative of the top is negative 2x squared. No, sorry, just negative 2x. Negative 2x times the bottom, y squared. So derivative of the top times the bottom minus the top times the derivative of the bottom, which is going to be 2y times y prime, because y is not our preferred variable, all over the bottom squared. Okay? Now when you get to this point, there's a key thing here you want to look at. Having a y that like this, y prime, in terms of x and y, no problem. But you don't really want a derivative in terms of x and y prime. So guess what? Same question. So y prime over here and y prime over here are going to be identical. So let's substitute. So we're on our way here. It's going to be negative 2xy squared. I'll get rid of some brackets here. It's going to be plus 2x squared y. And now we're going to put in negative x squared over y squared. And that's all over y to the fourth. All right. So we're not quite done yet. If you stopped right here, if you're doing AP and on the AP exam, that might be okay. But we need to practice simplification. That's a very important thing to do in calculus. So how do we do that? Well, you can see over here, this is a product right here. So let's take this y away with one of those y's. That makes sense, right? And because this is a sum here, I'm going to want to add this and this together. So why don't we right now just get a common denominator? This is over y. Why don't we make this over y, which is going to change this y squared to y cubed. Okay, because we multiply top and bottom by y. All right, so what does that do for us? Well, this is negative 2x y cubed, and then this is going to be over here minus 2x to the fourth, and all these things are going to be over y. Don't forget, it's all over y to the fourth. Right? So when you get to this point, you keep going, and when you divide by two things, it's the same as dividing by their product. So let's do that one step at a time here. Let's rewrite this up top. Yeah, we're going to factor that in a minute. But this is going to be over y to the fifth, okay? Almost there. Almost there. Take out a negative 2x. And I'm left with what? Y cubed minus x cubed. Sorry, plus x cubed all over y to the fifth. Now that looks really good, doesn't it? It does look really good. But one more thing you want to look at. When you get down to the very end, you think you can't factor, you can't divide out common factors anymore, is you want to go back and look to see if there's anything in this expression right here that is familiar from the question or that has already been defined as something else in the question. And of course, if you look at this expression right here and we go back to the top, guess what? You see it right there. What is it equal to? It's equal to 5. So yes, you should go that final step here now and do this. Y double prime, negative 2x times 5 over y to the fifth. And this finally becomes negative 10x over y to the fifth. And that is your solution. So there's a few little things in there that you'll need practice on. The simplification for sure. But as long as you understand the premise here that the second derivative is simply the derivative of the derivative, then that's not a big deal. So we did a little substitution right here, right? A little substitution there. And we did lots of simplification and another substitution over here to finally get this as our final answer here. Okay, so I hope that helps. It's the introduction to higher derivatives. Again, higher derivatives in polynomials is awesome, really easy. Not so much if we don't have a straight, polynomial function, but doable. All right.